Thank you for the introduction. My name is Sujit, and I am a PhD student at IIT Kanpur. And this is a joint work with my advisor, Subhajit Roy. Okay, so let me get started with showing you a logical formula in first order logic, which has a function called bar. So for this function bar, we may either do not have a logical semantics available, or it may be hard for us to encode bar in a logical formula. So for example, it may be an external library call, an web API call, or a machine learning model. So such functions, we denote it as closed box function in this paper and the presentation. So for simplicity, take this function, take this example as a function definition. So this function does nothing but simple multiplication. But in our setting, we will not have access to the definition. We'll only have the access to the interface of this function. So our problem statement is we want to test satisfiability of this first order logic constraint, which contains closed box functions. So there are certain assumptions regarding this closed box function. So the first one is that it must be functional, and we must have an input-output Oracle interface available, so we can query over the input-output data. So the next question is, can we not model it with a UF theory, and so sort of approximate with a UF theory? But we can do so and solve with the SMT solver, extract a model. But however, that may not be a valid model with respect to the function definition bar. So in this paper, we propose our tool Sādhak, which can solve queries over such closed box constraints involving such closed box functions. So Sādhak takes inputs and logical formula encoded in SMT-lib and the input-output Oracle interface, and it then gives out a model which is a valid, satisfiable model for this constraint. So this is the way we encode it in our tool. So this is an encoding in bit vector theory, and we sort of declare it as we have a keyword, declare CB to declare bar to be a closed box function, and we assume that the interface is available to us. So there are two main contributions of this paper. So we first introduce a theory called CB theory to support closed box functions in SMT solving. And we also introduced a new algorithm. So it's called conflict-driven fuzz loop algorithm to solve this closed box constraints. So this is the signature of the CB theory. So it's very similar to signature of other theories. So I'm just going to highlight two additional attributes that we have provided. So FCB is sort of defines the closed box functions, and we have another attribute R, where we provide the different translation schemes for translating different sorts and expressions into a program. So now I'm just going to walk you over the basic blocks of our algorithm. So we start with a constraint, then we perform a step called segregation, where we sort of filter out the pure SMT terms from this closed box function. So we sort of split into two sets of constraints. So one set which goes to the fuzz engine, which involves all the closed box terms, and then we send the pure terms to the SMT engines. And then the fuzz engine try to find a partial model, which it then sends to the SMT engine. And if SMT engine finds happy with that partial model and all the constraints in the SMTs are consistent with it, then we can just return that model. Otherwise, if it detects a conflict, we sort of analyze it and then propagate the reason why it was a conflict to the fuzz engine. And the fuzz engine can go on finding a new partial model. So we call this loop as a conflict-driven fuzz loop. So next, I'm going to show you every step of this algorithm with an example. So take this example constraint where f is a closed box function here. So the first step of the segregation is to purify. So we introduce new variables. So here we introduce z and we equate it with f of xy, and then replace all other occurrences of f with this variable z. And then we split into two set of constraints like this. So first we rewrite the function f as a UF term and send it all constraints, send this entire constraint to SMT engine, and then we only take out the term that involves close box function 2 and give it to the fuzz engine. So this is how the segregation step works. And okay, now we have two set of constraints, the one set with the SMT engine and other with the fuzz engine. So fuzz engine will try to generate a partial model. In this case, say it generates x0 equals 0, y equals 0, and z is 0. And it propagates to SMT engine, but there is a conflict here. So SMT engine will propagate this conflict to fuzz engine, and also it will learn some new fact about the closed box function f. In the next iteration, with the new clause x less than y, it also tries to generate. Sorry, I think there is an issue. Okay. So it tries to generate a new example, and then also finds a new conflict. And then it keeps on going in the same way. The SMT engine propagates the conflict and learns some new facts. And in this iteration, it gets a new model, which also conflicts with some other clauses in the SMT, and then it also learns a new fact. At the end, we get a model which sort of, you can see, consistent with the SMT engine. Now the fuzz engine can just propagate this model to the SMT engine, and then SMT engine can now give a model which is valid with respect to all the constraints modulo the closed box function that we didn't have definition for. So in this case, the function f was nothing but the simple multiplication ratio. So I'm just now walk you over how this fuzz, the internal structure of this fuzz engine. So the fuzz engine takes the constraint encoded in some theory, in this case a bit vector, and we also provide some translation schemes to such that the compiler in the fuzz engine translate down into some program, in this case, let's say C code. Now you can see that a crashing input for the C code is nothing but a satisfiable solution of this input formula. So we give the C code to the fuzzer and try to find a crashing input, which satisfies this constraint. So I'm going to show you some related works that have been done in this regard. So one was the tool Delphi. It was published in VMKI 2022. So this technique is purely SMT driven. So they take the SMT constraints with closed box, but they solve the constraint assuming the closed box to be UF terms, and then get a model, and then try to validate that model whether that is consistent with respect to the closed box function or not. And if it is a consistent model, then you just return with sat and return the model. Otherwise, you block that model by learning new fact about the UF term. And if you find any conflict, you can return with unsat. So the other work, which came out in ISTA 2019, in the tool named Colossus. So it takes the SMT constraint and compiles everything down to a C program, and then fuzz the C program. And if they found a satisfiable solution, you can just return that model, or you just exit with a timeout. So we implemented CDFL and this fuzz only technique into our tool Sādhak. So if you see the green cactus plot is the CDFL algorithm, and the red one is the fuzz only technique. And the blue and the red one blue and the maroon one are the performance of the tool Delphi. So you can see that our technique were able to solve more benchmarks out of 107. 107 we are able to solve in the CDFL mode around 101, and so I'm just showing you a part of our evaluation details, so you can find more on the paper. Yeah, so to conclude that in this paper we have introduced a closed bus function theory and a conflict-driven fuzz loop algorithm, which uses fuzzing in combination with SMT solving to able to solve constraint with closed box functions. And in the artifact, we have provided the implementation of a tool, Sādhak, which is built using CBC for SMT solver. And there are new 95 benchmarks which involves in SMT as SMT lib queries, which involves this closed box functions. So with that, I will stop my talk. If you have any questions.
Questions?
Can you say more about the particular fuzzer you used? Did you try different ones, or you just assumed they all would perform the same?
No, so the fuzzer that we used is AFL++, and we also tried with HOMFuzz initially, but we found that AFL++ worked better with the constraint that we had.
And what timeouts did you use for the fuzzer? When did you give up? And
so can you repeat?
what timeouts did you choose for the fuzzer?
Oh, the timeout was 600 seconds. So yeah. And
Did you play with that at all, or was that the first timeout that you picked?
No, yeah. So there are. You're saying that did we try with different timeouts?
Yeah, if you had a longer timeout, there might be more that the
so,
fuzzer would have found, but then of course you have a longer timeout.
Yeah, so the benchmarks which were timing out to 600, we tried to increase it, but we didn't find like around 1,000 seconds, but still we didn't find out that getting solved.
I'm asking a lot of questions because we have a lot of time. So, for your benchmark, did you have a mix of formulas that were both SAT and unsat, and how did your performance get affected by?
So here in this case, we all had the benchmarks which were all satisfied for checking for satisfiability only. So we can't say unsat for many cases. So we are saying that assuming that this closed box functions to be functional. So if you check with the UF theory and this unsat, so you can just return with unsat. And the other cases is that if you able to find some conflicting facts that you can't resolve, then you can also return with unsat. But those benchmarks were hard to sort of find. So we only tried it on satisfiable functions.
Thank you.
We have plenty of time for questions, so please don't be shy about asking questions for this round.
Thank you for the talk. I'm not an expert in fuzzer, so maybe it's a very naive question. So I see that every time you are getting a new model, the domain is infinite in this case.
Yeah.
So how do you guide it towards the correct direction? Can you comment on that?
Yeah, so we have sort of built it inside the UF theory solver. So there we can sort of, so there is this inbuilt equivalence class finding algorithms. So you can sort of find variables that are equivalent, so you don't need to include that in your input for the fuzzers. So you also can, there is a constraint where you have some assignments to constants that also you can eliminate. So this type of optimization we have discussed in the paper, so we can just reduce down the input space to a lot, then the fuzzer can work a better way. So
if I can add something, so the fuzzer also learns new facts. So if you look at CDFL, it keeps on learning new facts about the SMT part of the constraints. And that is sort of a guidance that the fuzzer gets to,
Okay, okay.
to sort of converge to a model that is more amenable to the lesson solver being able to complete it.
Makes sense. Thank you.
Hi, so I apologize. I didn't quite understand what you were saying about unsat. So if my formula is unsat, is it possible for me to like keep needing to query the function an infinite number of times to determine that it's unsat?
No, no, no. If your formula is unsat, so we also assume that. So I said assume that is to be functional. So if you solve it with that close box as a UF term and you find unsat, you can just exit with unsat, right? You don't have to go through the loop. So that part is there in the algorithm. So you can just exit there from there.
Okay, thanks.
Thank you for the talk. This is interesting work, and I'm wondering about if you have any thoughts about future applications for this work. I imagine it could be quite useful for program synthesis applications, and I have a second question too afterwards after this question.
Okay, yeah. So I mean, you're right. There are applications in program synthesis with respect to the closed work operations, and also any such components in the program you can think of that is hard to, I mean, if you sort of create a verification condition and that may blow up, right? So you can just keep it as a sort of Oracle interface and then keep on querying to find a satisfiable solution. So yeah, so maybe big ML models that if you're a programmer sort of using some big ML models, you can't really encode it in a logic form, then you can just keep it as a Oracle interface and then keep on querying to find some satisfiable solutions. Yeah.
Sure, very cool. And then my second question is, and I think that was touched on a little bit, but have you explored at all or thought about how maybe you could combine like conflict-driven learning? I know there's been some work on like conflict-driven learning for program synthesis. Maybe you could do some stuff like synthesizing further constraints from the information that you're getting from your fuzzer to maybe improve the performance of your SMT solver as a whole.
Yeah, I think I didn't get it properly, but yeah, we haven't thought really on this direction of synthesis, but yeah, this is something that we want to explore here.
Sure.
Do we have any other questions? We have plenty of time for questions.
Very good talk. I mean, this is not like a question, it's more like a suggestion. What I'm thinking is that, I think you mentioned it, I think what happens in many cases is that you have a very big system, and there's even like a lot of work on like having some kind of neurosymbolic things going on. Now, you can have a combination of a programs and a machine learning component, and you have some end-to-end system property you want, and you can probably design the logic of programs and encode it in the SMT query you are doing, but then you want to have some conditions on your maybe machine learning component that's going to be synthesized in a black box manner. And I'm wondering, because currently you only synthesize 1 points, can you synthesize a set of points which acts as a guard that says that, okay, I need to get the machine learning model that works well for this set of inputs, and then my property holds for the full system?
I don't know if I understand.
So
yeah, if you can.
Yeah, so that's a good suggestion, and we have done it for not this work, but other work we have done something similar. Like we have sort of the closed box component, we have used the convolution neural network as a closed box component, and we try to see the rest of the constraints and still work with the component and come up with interesting things. What is suggesting is a very interesting idea. So essentially, you're saying in some sense sample over the possible values modulo the complex machine learning model that you have, and get some sort of lemma over the behavior of this model.
Yeah.
It would be interesting. Yeah.
Basically, you want to synthesize what condition I need
Okay.
for the model that I synthesize the model such that the overall system works as well.
More questions from the audience? I had one question. So you mentioned that you can only, you basically assume like that they're functional. So that means you cannot handle functions with side effects. Why is that a fundamental limitation? Why couldn't you model functions with side effects as something that turns like that has multiple return values?
Yeah, I think.
So one trick that you can do to convert such things is basically use some sort of closures. So sort of package the state and make it as an input to the function, and then it becomes functional. So that is something we have been doing in other series of work, but here we assume that I would say the client would have done something similar to make it pure in some sense. But agreed, yeah, I mean, that sort of thing can be done. But in this particular work, the one reason we sort of said that the function is pure is that it is very easy to sort of say something is unsat if even with the functional axioms, the system turns out to be unsat. Then it is.
But from a fuzzing perspective, that assumption does, like impose a lot of limitations on where it can be used.
Sure. I take it. Yeah, that makes sense.
Another question I had is like on this slide, I see you mentioned that it's built on top of CVC4. Is there a particular reason for that? Or is there a certain CVC4 feature that you're using? Or, could you have implemented it on top of like Z3 or some other SMT
It was a
solver?
bit easier to engineer it in CVC4 compared to Z3. So initially I started looking at the Z3, but the CVC4 I found it a bit modular to include, and there are other features we can.
Okay, so no fundamental reason
not-
from an
no
engineering
fundamental reason, yeah,
perspective,
right.
I see.
Pure engineering reasons.
I see, okay. Any other questions? Okay, seems like we've converged on the questions, but since people are moving, back and forth between different sessions, so let's take a 5-minute break and let's restart at 2:30 with the next talk.